Okay, so we have one more type of reaction to finish. Last class we looked at single displacement reaction, activity series. Remember the activity series of metals, the table we looked at? And the metals on the top can displace anything below it, but if the metal is below, then it cannot displace something on the top, right? Now, the last type of reactions are called combustion reactions. So the other categories which we have learned, combination, decomposition, single displacement or double displacement. Those are the four major classes. This is a fifth class which may not fall into one of those. And combustion reaction, a substance reacts with oxygen and it will burn and produce a flame. So any reactions involving oxygen are not combustion reactions. The conditions are that a substance, first of all, oxygen should be there. That is one requirement. The second requirement is that it's a burn reaction, or in other words, it would always produce some kind of a flame. Then only it can be a combustion reaction. Another way of identifying a combustion reaction is, that is, if it doesn't say specifically it produced a flame or not, but you can see that oxygen is one of the reactant. Look at the products. A combustion reaction always produce carbon dioxide and water. Those are the products of a combustion reaction, okay, for a complete combustion reaction. So that is why the picture shown here is your Bunsen burner, which you always use in the lab. And what happens in Bunsen burner is this particular reaction. You have methane gas which reacts with oxygen. Of course, you know that it produces a flame. You have seen that. And look at the products, carbon dioxide and water. Okay. Now, in the lab, of course, you might be thinking, when I use the Bunsen burner, I don't see any water coming out of it. What is the physical state of water in this reaction? Gaseous. Or you know that this reaction, when it burns, it produces intense heat, right? Because of that heat, the water molecules which are produced, they are produced in the gaseous state. Of course, water vapor, it doesn't have any color or any odor, correct? So it would also escape into the air, just like the carbon dioxide. That is why you don't see water coming out of Bunsen burner. But the products are always water and carbon dioxide. And the reaction is also given in a pictorial way, showing CH4 molecules and O2 molecules producing water and carbon dioxide. Now, the most common combustion reactions are burning hydrocarbons. What do we mean by a hydrocarbon? Can you give me an idea by just looking at that name? Hydrocarbon. Something which contain hydrogens and carbon. Those are hydrocarbons. And we have a big series of compounds which are called hydrocarbons. Most of our fuels, they are all hydrocarbons. The gas we put in our car, that is a hydrocarbon, okay? So most of the combustion reactions involve burning hydrocarbon, or some hydrocarbons contain slight amount of oxygen also. So the products, as I said, always carbon dioxide and water. Here is a higher hydrocarbon, C8H18, and that also reacts with oxygen and producing carbon dioxide and water. So as we use a higher hydrocarbon, of course the amount of oxygen you require for the reaction is higher, and the amount of products produced are also higher, right? That is understandable. If you use high amount of fuel, you will get high amount of products. The same philosophy. Now, combustion reaction, as I said, we are not going to go into any other details. All you have to remember is combustion reactions means burn reactions. Oxygen is a requirement, and that is why when we use Bunsen burner in the lab, we need air. That valve you rotate to get the air. You have noticed that when you just play with it. If you go the wrong way, if it doesn't get sufficient oxygen, then the flame becomes yellow, and I tell that don't use the yellow flame, right? Yellow means it doesn't have sufficient oxygen or sufficient air, so it's burning incomplete. Incomplete burns are represented by the yellow flame. When it has sufficient oxygen, you will see the blue flame, which doesn't which uses the sufficient amount of oxygen, so it is completely burning. That is when you see the blue flame. Okay, now the last topic in this chapter, representing reactions in aqueous solutions. So this section involves little more, what do I say, just not only just looking at the reactions and balancing it, we are adding another difficulty in here, okay, a level of difficulty. So let us concentrate. So when reactions occur in water, soluble ionic compounds exist as separate ions. We know that. When we looked at electrolytes, non-electrolytes, right? Ionic compounds are all electrolytes because when they dissolve in water, they separate into its ions, and ions have charges. Therefore, they can move along and they can conduct electricity. So, we know this already. Soluble ionic compounds exist as ions, not grouped together with each other, as might seem to so from the equation, sometimes called a molecular equation. So we are going to learn about different types of equations now. So far, all the chemical equations we have seen, they all fall into this one category called molecular equations, or a chemical equation which shows the molecular formula of the reactants and molecular formula of the products. So this reaction, silver nitrate and sodium chloride reacting and forming silver chloride and sodium nitrate, that reaction which is given there is an example of a molecular equation. It shows the molecular formula of reactants and the products, and that is balanced. Now, when we put NaCl we know sodium chloride, it is a solid white powder. When we put that into water, we know that it dissolves, right? When it dissolves in water, is it still staying as Na and Cl together? Are they staying Na and Cl together? That's my question. No, they would separate into Na plus and Cl minus, right? Even though they separate into Na plus and Cl minus, we still write that as NaCl together and Aq. Do you see the difference? This is what this sentence means. Not grouped together with each other as might seem so from the equation. In the equation, we write still Na and Cl together. We are not writing this as Na plus and Cl minus separate, right? We still write them together just to differentiate between solid NaCl and NaCl dissolved in water. We would just put the Aq in parenthesis, showing that NaCl is dissolved in water. But actually, what does it look like? This is solid NaCl. Let's say it's a chunk. We put it into water. And in water, this is how they exist. It has separated into Na plus and Cl minus ions, right? But when we write it, we write that as NaCl aqueous. Everyone is with me so far? Okay. Now, this is the next type of equation. The name is Ionic equation. Now, what is the difference between Ionic equation and molecular equation? An Ionic equation shows soluble ionic compounds as separate ions. So, the previous equation, let me just write that equation one more time so that we don't have to go back to the slide. So, the equation we saw that was silver nitrate aqueous plus NaCl aqueous giving us silver chloride, which is a solid, and NaNO3 aqueous. This was the molecular equation we have seen in the previous slide, right? Now look how we write the ionic equation from this molecular equation. Every species which is dissolved in water, every species which has AQ in parenthesis, now you write them as its separate ions. You know that AgNO3 aqueous means silver nitrate dissolved in water, and of course silver nitrate is an ionic compound. It contains a metal ion, silver. We know that ionic compounds will dissociate into its ions, so we are just showing that. Ionic compound silver nitrate is dissociated into Ag plus and NO3 ions in water. That's all we are showing. Similarly, NaCl aqueous is dissociated into Na plus and Cl minus ions. Now, the right side of the arrow, note that AgCl we are not going to break it. Why we are not breaking it? Give me the reason. It is a solid. It is not a soluble ionic compound, right? See what it says, soluble ionic compounds. We can separate only the soluble ionic compounds. And how do we identify what are the soluble ionic compounds? Whatever species which has an AQ in parenthesis, they are soluble in water. So we can separate only them. AgCl, since it is a solid, we do not touch it. Again, NaNO3 is aqueous, so we have to write Na plus and NO3 minus. So as the next line says, insoluble compounds do not exist as ions. Now here is the new term, spectator ions. Spectator ions are ions that occur on both sides of the equation. Or spectator ions, as the word suggests, they are just spectators. They are just hanging out there. They are not participating in the chemical reaction. If you go for a match, you are just, sitting there and watching, then you are a spectator. You are not playing, right? So we can think a chemical reaction as this way. A chemical reaction, the molecular equation shows everything, but that doesn't mean that all of them are playing in the reaction or all of them are actually doing something in the reaction. Some of them are just hanging out on both sides just to watch. Those are called spectator ions. Now, how do we identify spectator ions? As it says, spectator ions occur on both sides of the equation. So once you have your ionic equation, check both sides of the arrow one by one. Pick up the first one, Ag plus. I see an Ag plus on the left side. Do I have an Ag plus on the right side? Where is the Ag plus? AgCl is not separated into ions. What does it say? Insoluble compounds do not exist as ions. So on the right side, Ag is in ionic form? It is not. What we mean by that is exactly as we see here. Here I see Ag plus aqueous. That's what I want to see on the right side. Do I have one of those on the right side? I do not. So Ag plus is not a spectator ion. Next one, NO3 minus aqueous. Do I have NO3 minus aqueous exactly as it is on the right side? Yes. I do. So this is a spectator ion. Here it is. This is a set of spectator ion. Okay, the next one, Na plus aqueous. Do I have Na plus aqueous on both sides? Yes, I do. So this is my second set of spectator ion. How about Cl minus aqueous? Do I have Cl minus aqueous on both sides? I do not. So that is not a spectator ion. So this is how you identify the spectator ion. Okay? From the ionic equation, look for ions which exist exactly the same way on both sides. Now, once we identify the spectator ion, we get the third, we have another, let me just finish this, guys. So once you identify the spectator ions, you get the third type of equation, which is called net ionic equation. So net ionic equation is the chemical equation which shows whatever species left after eliminating the spectator ions. So from this equation I have identified the spectator ions, I eliminate them and I write out what are left. What are left? On the left side I have Ag plus aqueous, which is not a spectator ion, and I also have Cl minus aqueous, which is not a spectator ion. On the right side of the equation all I am left with is AgCl solid. Everyone see how I got this equation? I just eliminate the spectator ions, or in other words, now you are really focusing on who are the players in the chemical reaction, not who are just hanging out on both sides. Whoever is hanging out on both sides, throw them out. Keep only the players. You get the net ionic equation. Okay? So, we will practice more on this. So, molecular equation shows all the molecular formulas with their physical states. Then you can write ionic equation where all the aqueous species will be split into its ions. Remember, we split only aqueous species. We do not touch solids. We do not touch liquids. We do not touch gases. Okay? So when you write the molecular equation, looking at the solubility table, you figure out your product, what are the physical states. If you have anything gas, solid, you might find liquid because some chemical reactions produce pure water, acid-base neutralization reactions. It produces water, and when water is produced as a product, it is in liquid state, right? We put L in parenthesis. So if you see G, L or S in parenthesis, don't touch them. You cannot split them. So the only thing left is anything with AQ. Anything with AQ, split them into its ions. That's what is the ionic equation is. Once you get the ionic equation, you can carefully check on both sides. Who are existing on both sides? Eliminate them. Or identify them, like I am circling them, or I can very well put like, a line over just to identify them. Your goal is just to identify the spectator ions. Then eliminate them. Whatever is left will give you your net ionic equation. So we are going to practice more. First, let us try to identify. Here is an ionic equation. This was the previous equation we just played. Right? Yeah. Okay. Well, that doesn't make much sense. Let me see if I have. Well, there it is. We identified, right? NO3 and Na plus exist on both sides as ions. So those are the spectator ions. Okay. So there it is. Since the spectator ions do not change, or they just exist same way on both sides, we can leave them out of the equation, and when we leave them out, we get the net ionic equation. I have shown you this in the previous slide itself. So the net ionic equation is, we eliminate NO3 and Na plus from both sides. So what are we left with? That is your net ionic equation. Okay, so this is another example. Barium sulfate used in the white pigment lithopone can be prepared by mixing solutions of barium chloride and sodium sulfate. Write balanced molecular, ionic and net ionic equations for this reaction. You will have questions like that in your next exam, okay? So we need to start from the scratch. All we know is our reactants. So you need to know how to write the formula, then we have to predict the products, then we have to find out what are the physical states of the products using the solubility table. Then we need to balance the equation. Then only we get the molecular equation. Once we have the molecular equation, then it goes easy, right? You can just split all AQ to ions. You get the ionic equation. Then identify spectator ions. Eliminate them. You get the net ionic. Don't worry. We are going to do it step by step. How about, let us see, what are the reactants? Can be prepared by mixing solutions of. That means both reactants are, solutions means what will be your physical state? AQ. So both solutions, barium chloride and sodium sulfate. Let me get a new screen. And what? Yes. It will clearly say that liquid. It won't say solution. Solution, if you think about what is the meaning of the word solution, something dissolved in a solvent, right? Liquid is a pure form. See the difference? But solution, the word itself says that solute, dissolved in solvent. That is how you make the solution. So something is dissolved. So solution means it is aqueous. So take that clue. Good question. Solution means it's aqueous. If it is a liquid, it would clearly say in your question itself. Okay? Liquid, it creates liquid water or liquid something. Okay, so what were our reactants? Let me write it down. It was barium chloride and sodium sulfate. Where is my pen? I just made it red. No, yellow, that's why. Okay, ink color. Let's go with red. All right, now I can see. So, we have barium chloride. We know that it is AQ, and we are mixing that with sodium sulfate. The question says that is also AQ. This is all the information we have, that this is your starting point. That's all the question says. Now, first thing is we need to convert these two names into formulas. Come on, you guys all know this. Help me out. Barium is Ba2 plus, chloride is Cl minus. So how many barium, how many chloride I need? 2 chloride for 1 barium. So the formula is BaCl2, and we know that that is aqueous, plus, how about sodium sulfate? Sodium is Na plus, sulfate is SO4 2 negative. So how many sodium you need with each sulfate? 2. So the formula would be Na2SO4. We know that is also aqueous. Okay, so we got our reactants. Now let's write the products. Double displacement reaction. Predict the products, please. BaSO4 and NaCl. Okay, is that equation balanced? It is not. What is wrong? Cl and Na numbers, right? We have 2 Cl and 2 Na on the left side. So right side also we need 2. So what are we going to do? You put a 2 in front of NaCl. Okay, now let's figure out the physical states of the products. Look in your solubility table. You may have this one worked out in the book, but please don't just look at the answer like that. You won't learn. You need to know. You need to train your brain, right? How you do this. So take your solubility table and figure out what are the physical states. What are the rules for barium and sulfate? Most sulfates are soluble. Do we have exceptions? Okay. Is BaSO4 is an exception? Yes. That means BaSO4 is a solid. How about NaCl? NaCl is soluble. If you look for the rules of chlorides, most chlorides are soluble. There are exceptions, but Na is not one of them. Right? So NaCl is aqueous. Good. Now, what equation is this? What is the name of this equation? Molecular equation. So now we got our first equation, which is the molecular equation, which shows the correct formulas of all the species, products and reactants, equation is balanced, and their physical states. This is your first step, writing the molecular equation. Now we need the ionic equation, IE. So, when we write the ionic equation, what is it we have to remember? Separate every species which has AQ in parenthesis into its corresponding ions. Do we touch anything with solid, liquid, gas? We do not. Alright, let's start. BaCl2 has AQ in parenthesis. How do we split them into its ions? Ba what plus? 2 plus, and now AQ goes for each of them. So Ba2 plus AQ plus Cl minus, how many Cl minus I have in BaCl2? 2. So put the coefficient 2 there, and that is also aqueous. Good. Go for the next one, Na2SO4. Yes.
Why don't you just put the subscript down?
Because that says Cl2 minus. That is wrong. There Cl2, when they exist together, it's a gas. It's not an ion. When Cl is in ionic form, it can only form one negative charge. So it is Cl minus ions. How many of them? 2 of them. Okay? When you write the ions, you have to follow that charge rules. Okay, Na2, yes. Yes. Yes, but you have 2 of them there, right? Yes. Yes. Note that from the molecular equation, once the equation is balanced, in water we are showing that BaCl2 exists as Ba2 plus ion and 2Cl minus ion. That's all we are trying to say there. We cannot change the numbers once we balance the equation. Okay? Because BaCl2 aqueous means what? BaCl2 is dissolved in water, and we know that when it is dissolved in water, they separate into its ions. So what are those ions? That's all we are trying to write down. Okay, how about the second one? What are the ions? Na plus ions. Do I have only one there? I have 2 of them. So 2 Na aqueous. And what is my other ion? SO4. What is the charge of SO4? 2 negative, aqueous. Good. We finished the left side. Let's go to the right side now. BaSO4 solid. Do I do anything with that? No. I will not. So I will write that exactly as it is. BaSO4 solid plus, what happens to the 2NaCl aqueous? I have to separate them into ions, right? That is an aqueous species. How many sodium ions I have there? 2. So 2 Na plus aqueous, and how about the Cl minus ions? How many I have? 2 Cl minus aqueous. You got your ionic equation. We split every aqueous species into its corresponding ions. What is the next step? We need to look for the spectators. So spectators are ions that exist on both sides of the equation. So let's start with the first one. Ba2 plus aqueous. Do I have Ba2 plus aqueous on the right side? No, I don't. Right? Okay. How about 2Cl minus? Do I have on left side and right side? Yes, I do. So that is one set of spectator ion. I am eliminating them. How about 2 Na plus aqueous? I do have 2 Na plus aqueous on both sides. I eliminate them. Do I have an SO4 2 minus on both sides? I do not. So I identified my spectator ions. They were Na plus and Cl minus ions, 2 each. I eliminated them. Now I can write my third equation, which is, by the way, where is my pen? Oh, there it is. Which is net ionic equation. How do we write net ionic equation? What is the difference between ionic and net ionic equation? Net ionic equation does not contain the spectator ions. So once you identify the spectator ions, all you need to do is write down whatever is left in the ionic equation. That will be your net ionic equation. So Ba2 plus is left in the ionic equation, right? So we use that, Ba2 plus aqueous, and I will not include 2 Cl minus and 2 Na plus because those were spectator ions. What else is left on the left side of the equation? SO4 2 minus. So anything left on the left side? No. What about the right side? You have BaSO4 solid. That is your net ionic equation. So this is how we write all three types of equation. Yes.
Would it be easier to just look for the solid and see what it's made of instead of looking for every one?
Usually that's what it will come down to. But how do you write the ionic equation? I mean, if the question is asking write molecular, ionic and net ionic equation, then you cannot skip that identifying spectator ion step. You should use that philosophy as a checkpoint. Let's say in your equation you identified something solid forming, and 99.9% of the time your net ionic equation will be the formation of that solid. Okay? In case when you identify your spectator ions and when you write the net ionic equation, if you are not getting it, use that as a checkpoint to go back and check what you did wrong. Okay? Don't just use that as your tool to write down net ionic equation, because when you write the ionic equation you might miss something if you don't pay attention. So use that as a check tool. Okay? Let's see, I might have, so okay, here is the slide which describe all this process we have done. So both the reactants are electrolytes, so dissociate into ions. So possible formulas, solubility rule says that NaCl is soluble, BaSO4 is insoluble, so we get our molecular equation. This is what the thought process we followed, right? So the slides also shows you again everything, and then BaCl2, Na2SO4 and NaCl all are strong electrolytes, so they are aqueous species which we separated into its ions, and we get the ionic equation. And then we identified the spectator ions which are Cl minus and Na plus. We eliminate them on both sides and we get the net ionic equation. Let's see, I might have another example. Yes, here the equation is given to you. Identify the spectator ions and write the net ionic equations from the following molecular equation. So this is a balanced molecular equation given to you. So we need our ionic equation, then we will identify the spectator ions and we will write the molecular equation. So ionic equation, I am ready to write this is the molecular equation, we all know that. I am ready to write the ionic equation. Help me, what happens to Cu? Nothing, because it is solid. Okay. Plus 2AgNO3 aqueous, 2Ag, what is the charge of Ag? 2. Why? Look at the formula, AgNO3. NO3 is nitrate. From the chart you know that it is always 1 minus. So 1 nitrate has 1 silver means what is the charge of silver? One nitrate has 1 minus charge. Nitrate is NO3. So Ag has to be 1 positive. So 2 Ag plus aqueous, and how many nitrate ion I have? 2. 2 NO3 minus aqueous. Okay. Right side. CuNO3 twice aqueous. Do I split that? Yes, I do. Okay. What are the ions? Cu. What is the charge of Cu? 2 plus, because each Cu is taking 2 nitrates, right? And nitrate is only 1 minus. So 1 Cu needs 2 nitrate, means Cu has to be 2 plus here. So Cu2 plus, and how many nitrates you have? 2 nitrates, 2 NO3 aqueous, plus how about 2 Ag solid? That stays as it is. Okay. Now Thomas, do you see why we cannot just look at the solid and write the net ionic equation? Because in this reaction, what would you write? Right?
If there's no solid in the first one.
Yeah, that's why I'm saying use that as kind of a check tool. Don't just use that to write the equation down. Okay? Alright, so let's identify the spectator ions. Cu solid. Do I have Cu solid on both sides? No. I have? Okay. 2 Ag plus aqueous. Do I have 2 Ag plus aqueous on both sides? Where is it on the right side, Senia? Tell me. One is 2 Ag plus aqueous. Here what we see is 2 Ag solid. Are they one and the same? They are not. Okay? They are not. One is Ag plus ion dissolved in water. The other one is pure silver metal. They are not one and the same. So Ag plus is not a spectator ion. How about 2 NO3 minus? You see that exactly the same way on both sides? So that is the spectator ion. So you identified the spectator ion, which is only 2 NO3 minus in this reaction. So now you can write down your net ionic equation. We identified the spectator ion, eliminate that. Let's write down the net ionic equation. So the net ionic equation is Cu solid plus 2 Ag plus aqueous, giving us Cu2 plus aqueous and 2 Ag solid. What type of a reaction is this? Look at the equation, single displacement reaction, copper solid displacing silver ions, because copper is above silver in the activity series. So if you put copper solid into a solution containing silver ions, it will take the place of, that's what, you can look at the molecular equation and figure out that, right? Copper solid taking the place of silver, so copper nitrate and silver will come out. So copper is displacing silver, it is a single displacement reaction. So in that single displacement reaction, if you really look into the core, who actually played? It's only copper and silver ions displacing each other. Nitrate is basically spectator ion. Nitrate doesn't matter whether it's with the copper or with the silver. As long as it's there in the solution, it's happy. No preference. Right? But copper and silver, yes, based on their activity, they displace. Okay, one more. Identify the spectator ions and write the net ionic equation from the following molecular equation. So, ionic equation, let's write that. 2 NaCl aqueous Help me guys and girls. 2 Na plus aqueous plus 2 Cl minus aqueous plus Ag2SO4. 2 Ag positive aqueous plus what else is there? SO4 2 minus aqueous. Good. Right side. 2 Na plus aqueous plus SO4 2 minus aqueous plus 2 Ag what is it? AgCl, what is the physical state? Do I split it? No. So I will write it as it is, 2 AgCl solid. Now identify the spectator ions. What are the ions existing exactly the same as both sides? 2 Ag plus? Where do you see 2 Ag plus on both sides? Check again. 2 Na plus I see, 2 Na plus here and 2 Na plus here. So that is one set of spectator ion. What is the other set? SO4 2 minus and SO4 2 minus. Not that here it is 2 Ag plus, here it is AgCl solid, they are not the same. Again 2 Cl minus. This is not Cl minus ions here, it is combined together, right? Okay, so what is your net ionic equation? 2 Cl minus Aq plus 2 Ag plus Aq forming 2 AgCl solid. That is your net ionic equation. Question so far? So, once again, you are given the molecular equation. If you are not given the molecular equation, of course, you know how to write the formulas and then predict the products. Use the solubility table to figure out what is the physical state of the products. Then, the next steps, only two things to remember guys. Split every AQ into its ions. Do not touch solid liquid gas. Only split AQ species into ions. That will give you the ionic equation. Then look carefully on both sides what ions exist on both sides. Only ions. Okay, don't just look at the symbol, oh I see Ag. No. What Ag is it? Ag plus or just Ag solid? They are two different things. On both sides, whatever exists exactly the same way, they are the spectator ions. And once you eliminate them, whatever is left will give you the net ionic equation. Alright, let me see, I think, oh one more, let's do one more example and then we will do a clicker question on this. So again, identify the spectator ions and write the net ionic equations from the following molecular equation. I won't say much, just tell me what to write. I am writing the ionic equation. If I am doing something right, I am just going to write whatever you say. If it is something wrong, somebody has to identify that and let me know. I won't say a word. What else? Keep going. Am I finished writing with Fe? What is missing? What? Uh-huh. There are 3 OHs, right? Okay. Three. Okay. Good. It's very hard. You have to do it your own, right? If everything I do for you, what would you do in the exam? That is why I said you do it your own. I'll just write it for you. Okay, now identify the spectator ions. Three Cl minus. Okay. What else? 3 NH4 plus also. Is there any other spectator ion? No. Alright. So give me the net ionic equation, please. Good. So I hope everyone, yes.
Can I finish copying?
Yeah, sure. So everyone has a good idea how to do this one? Okay. Of course, we will finish the chapter today. This is the last thing. So I will assign the homework problems also, and you will have more chance to do practice on it. Okay. Once again, as a summary, molecular equations will show all the molecular formulas with their physical states and balanced equation. For writing ionic equation, just split every species with AQ into its ions. When you split, yes, you have to pay attention to what charge is each ion is in and how many of them are there. Okay? If you don't show that, it is not complete ionic equation. Once you have the ionic equation, look one by one, both sides, which one exists exactly the same way on both sides. Just eliminate them. Whatever those species exists exactly the same way on both sides are called spectator ions. So if the question is asking what are the spectator ions, yes, whatever you are identifying as existing on both sides, that will be your answer. Now if you want to write net ionic equation, eliminate the spectator ions, write out whatever is left. Okay, take out your clickers. I thought you are going to throw that at me, Cody. I know you won't do that. I'm just kidding. What? Well, he had plenty of chances to throw things at me last year, right, Cody? He didn't do that, so I think I will survive.
You're safe.
I am, thank you. So, read the question carefully. I'm asking only what are the spectator ions. Identify them and choose the right answer, please. Everyone has clickers today? 20, right? $330. Ten seconds. I will stop at 3:30, okay? Okay, whoever has not answered, just click so that you get the attendance point. All right. How do you do this? What? Okay, separate the aqueous species. So, what do we have? 2Ag plus and 2NO3 minus plus, oops, Ba2 plus aqueous and 2Cl minus aqueous. Good. 2AgCl solid stays the same. Two plus aqueous and 2NO3 minus aqueous. What are the spectator ions? 2NO3 minus exist on both sides. What else? And Ba2 plus exist on both sides. Otherwise also, if you just look at the reaction, you see AgCl is a solid, right? Let's say if it's a multiple choice and you don't want to do all this work, then this is another shortcut to do this problem. You see that AgCl is a solid. So you know that whatever ions forming AgCl will not be existing on both sides, right? So Ag plus and Cl minuses are not going to be the spectator ions. Whatever is left should be the spectator ions. Maybe if that is too much for you, you just go ahead in the straightforward way. So you identify these are your spectator ions, and do we have a choice like that? C shows that Ba2 plus and NO3 minus ions. Yes.
Wouldn't C be wrong? It shouldn't be 2 NO3 minus?
Well, all I'm asking is what are the spectator ions? So you just want to know the name of the species. I'm not asking how many of them are there, right? Here why we have to show the numbers, because this is the ionic equation. An equation should show all the numbers, everything correctly. But all I'm asking here is what are the ions. So as long as you identify what ions, it's fine. You don't have to say how many of them are also present. Okay. So let's say if there was a 2 in front of here, doesn't make any difference. Yes.
If there was a 2 NO3 minus and an NO3 minus on the other side, would it just be 1 NO3 minus on one side?
Well, I don't think any, these questions also, guys, just to tell you this, the publisher send me for every chapter clicker questions. So I just copy the questions and put them into the PowerPoint wherever it is necessary. Okay. So I don't think they will put that much trick into, their goal is also not to trick you. So I don't think they'll make a choice that is Ba2 plus and NO3 minus and another choice which is Ba2 plus and 2 NO3 minus. No, obviously if something like that, then I won't ask you that question. Okay, because that's not the point, right? What we are trying to do is we are trying to identify what are the spectator ions. So it should be fine. So our answer should be, who said A? Okay, well, C is the right answer, and I see that A and D have been chosen as the answers. A, absolutely no chance, because AgCl is a solid, so Ag plus and Cl minus cannot exist on both sides. D, once again same reason, Cl minus cannot exist on both sides because it's been a solid on the right side. How about B? Well, Ag plus cannot exist on both sides because Ag is a solid on the right side. Okay, so I guess that's the end of this chapter. What? I will post that PowerPoint. I will post the PowerPoint only at the end of the chapter because otherwise all the clicker questions will get published, right? I don't want that. Okay, so we are going to look into the beginning of chapter 6. So at the end of chapter 6, we will have our second exam. Definitely that will be after you come back from your break. Okay, so what? What did you say? Now, when we come back, we will have our next exam. I mean, when we come back, I will probably give you the date, but keep in mind that whenever we finish chapter 6, next class will be our exam. Okay, covering chapter 4, 5, and 6. Now, chapter 6 is a continuation of chapter 4. As you can see the title, Quantities in Chemical Reactions. So, this is another chapter where we do problems only. Okay, and whatever problem solving, whatever techniques you learned in chapter 4 will be used here also. This is continuation of that. So we are going to add more onto that. So if you were doing, converting mass to moles or moles to mass as one problem in chapter 4, here that will be only part of the problem. Okay? So pay attention from the beginning. If you need to watch the class again, you have that option. So the topics we will be looking at is, what is the meaning of a balanced equation? So we balanced the equations in previous chapter. We learned how to do that, and we said it is because mass of conservation has to be followed. But we are going to look into more detail. What does those numbers mean? Then we will do mole conversions, mass conversions. We already know mass mole conversion, right? Then we will do something about limiting reactants. That will be a new concept for you. Then percent yield. Couple of times I think in the lab you have done the calculation without actually realizing what exactly that means. You had the equation given, you plug in the numbers, you calculated the percent yield. But we will see what does that mean. And then we have a little bit of energy changes and heat changes in chemical reaction. I know that only Tuesday lab get to do the calorimetry experiment. The Wednesday lab you guys missed it because the school was closed on a snow day. And we skipped an experiment, right? That calorimetry is actually the heat changes in chemical reactions part. So even though you didn't do the lab, you are going to learn the theory. And Tuesday guys who did the lab hopefully will understand what you did in the lab better. Okay? So these are the topics we are going to do in this chapter. So we are going to start with, what do we mean by a balanced equation? What is the meaning of it? So how can we predict amounts of reactants and products in a reaction, such as that at an internal combustion engine. We know that in an internal combustion engine, like the engines used in car, hydrocarbon, the gas we put in, will burn with oxygen and produce water, carbon dioxide, and then a lot of heat. And that heat is a form of energy, which is what we use to run our car. Okay? So how do you design all this? That is, what engine burns, what gas, with what ratio of oxygen, all those things. How do you decide all those things? Or how do we predict the amount of heat generated or absorbed in a reaction? In case of an internal combustion engine, of course, it will be heat releasing. There is humongous amount of heat released. So this is just, we are not going to go into details of any engine mechanical problems or anything, okay? This is just a schematic just to show you, in case if anyone is wondering, what is an internal combustion engine, or what do they do in my car? That's all. This is the only one slide we are looking at the engine. We are not going into ripping apart the engine and studying that. We will leave that for the automotive technology students. So, in an internal combustion engine, octane burns with oxygen to produce hot gases that push against a piston to do the work. That's what is basically, this is a single engine. Well, our cars are not single engines, right? I mean, they are, I don't know all those details, guys, so probably you guys know that better than me. All I know is the price of the car. Rest of the things my husband talked to the salesman. So, so I'm really bad in that, okay? So most of you might know better than me on this, so I guess I'm not going in there. So all it does is we put the gas in there, it burns with the oxygen and it produces a lot of heat, and we use that heat energy to push the piston to do the work or to move the car. Okay? Now, what point we are going to take from this is the amount of oxygen that reacts depends upon the amount of octane that burns. So it is a combustion reaction which goes on in every engine, and the amount will vary from engine to engine, right? We know that not all engine work the same way. Not all engine use the same amount of gas for same amount of oxygen. The ratio will vary. So that's what it says. The amount depends upon the amount of reactants available, and the amount of energy produced as a result also will vary, or also will depend upon how much octane burned with how much oxygen. Okay, so that's all we are going to concentrate on. So let's say here is a balanced equation, propane gas reacting with oxygen. It's a combustion reaction. We have the balanced equation given in the bottom, C3H8 plus 5O2, both are gases producing 3 carbon dioxide and 4 water, gases again because it's a combustion reaction. And we have the picture also given, how many propane, how many oxygen, how many water, how many carbon dioxide. Now, what does this tells us about the relative amounts of the reactants and products? If you just look at that balanced equation, one molecule of propane, well, there is no number before propane. So what do we assume? 1, right? 1 is most of the time invisible. We don't write 1 when it is. So start seeing that Mr. Invisible 1. Okay? So 1 is invisible, so we know, but it is there. So 1 molecule of propane reacting with how many molecules of oxygen? 5 molecules of oxygen producing 3 molecules of carbon dioxide and 4 molecules of water. That's what the balanced equation tells us, right? Or just by looking at that, you can say these are the number of molecules, or there is a particular ratio. So for every 1 molecule of propane, you need 5 molecules of oxygen. Then only that reaction will happen. And when they react in that combination, it makes all the time 3 molecules of carbon dioxide and 4 molecules of water. It is fixed. It is not 3.5 molecules of water or 4.5 molecules of water, it is 4 molecules of water. So, those coefficients in the balanced equation tells us about the relative numbers of the reactants that combine and products that form. As I said, the coefficient 1 is invisible, but we need to see that when we look into the mole ratio things, which you will see in a while. Now, so again, for every molecule of propane that reacts with 5 molecules of oxygen, 3 molecules of carbon dioxide and 4 molecules of water are produced. Now, this coefficients in the balanced equation tells us not only just the number of molecules, but we can just convert that into number of moles, or you can think of this reaction as every 1 mole of propane you need 5 mole of oxygen, and when they react in that way 3 moles of carbon dioxide is formed and 4 moles of water is formed. So instead of thinking of them as now molecules, those coefficients we are going to think them as number of moles. This next table will explain to you how can we reach there. Let's start here. This is where we started. We said just by looking at this reaction, 1 molecule of propane needs 5 molecules and it produces 3 molecules of carbon dioxide and 4 molecules of water. Now, let's assume I am doubling the amount of propane. So, instead of 1 molecule, now I have 2 molecules of propane. So, for 2 molecules of propane, how many molecules of oxygen I will need? 10. Makes sense, right? Because 1 molecule need 5, so 2 molecule will need 10. Right? So, when 1 and 5 produced 3 molecules here, if I double the amount of the reactants here, then should my product also double? Yes. So my carbon dioxide is now 6 molecules and water is 8 molecules. Now let's say instead of doubling, I am taking 100 times propane I started with. Instead of 1 molecule, I am taking 100 molecule. So 1 molecule needed 5 molecule. So 100 molecule will need 500 molecule. The same, right? Whatever change you are making here, the point is everything else also will get changed in the same proportion. Right? If I have changed to 1 to 100, then 5 has to be changed to 500. 3 has to be changed to 300. 4 is changed to 400. Now let's say instead of 100 molecule, I am taking 6.022 into 10 to the power 23 molecules. Remember that number? Avogadro's number, right? So I am using that many molecules of propane. So if I have one set of Avogadro's number of propane, how many sets of Avogadro's number I need for the oxygen? 5 sets, right? Say for example, if I start with 1 dozen propane, I need 5 dozens of oxygen, right? And I will produce 3 dozen carbon dioxide and 4 dozen water, right? So instead of the dozen, I am just using the Avogadro's number, that's all. Now, Avogadro's number by definition is number of molecules in 1 mole, correct? So when I use this many molecules of propane, mathematically I am using 1 mole of propane. And when this number gets multiplied by 5, I get 5 moles. When this number multiplied by 3, I have 3 moles. Similarly, I have 4 moles. So now you look at the balanced equation and the last line there. Each of those numerical coefficients, you don't have to go through this conversion every time, this logic every time. Once you understand this, it's not going to change, right? So every chemical reaction, those numerical coefficients you put in front of them represents how many moles of each of them are reacting and how many moles of each of them are produced. So those coefficients represents the mole relationship in a chemical reaction. So the process of determining the amount of the reactant or product from another reactant or product in a chemical reaction is called stoichiometry. And that's what this chapter is all about. Calculations on how can we predict how much, say for example, when you do the lab, how come those guys who write the procedure comes up with, start with 2 grams, then you get this much, all that stuff, or the solutions you use. I prepare all those solutions for you. How do I figure out how many grams I should take and dissolve in how much water to produce a solution which will be giving you this reaction, all those things. This is all those calculations comes under the general name stoichiometry. Okay, so we are going to go into a little bit detail of stoichiometry. Let me see. Maybe I should start this next class, because once I start, I don't want to leave you somewhere in the middle. Okay, so let's just stop right here and